Welcome to lecture number 10 in Multiple Antenna Communications at Linköping University. In this lecture, we will extend the analysis from the previous lectures to cellular networks. So we will talk about the basic structure and then important things around channel estimation, a new phenomena called pilot contamination, and then I will present the formulas for the spectral efficiency with maximum ratio processing in the uplink and the downlink. So first we should recall these coherence intervals that I talked about before. So we know that the channel is changing over time and also over the frequency domain. But we can divide the frequency domain into small intervals that we call the coherence bandwidth, and we call it BC. And then within such a coherence bandwidth we have a channel that is described only by a scalar number. But that scalar number is changing over time. But if we are zooming in at the particularly small amount of time, which we call the coherence time, the scalar number can be considered constant. And we call that coherence time TC. And then according to the sampling theorem, we can have BC times TC complex samples within one of these blocks, meaning that a signal is described uniquely with that number of samples. And that is the number of samples in a coherence interval, and we are using these ones to send the data and also to learn the channels. So everything needs to be happening within one coherence interval, and that is something we should remember. So in the previous two lectures I've been talking about these capacity lower bounds that we get in the uplink and in the downlink. And they were log2 or 1 plus some kind of signals to interference and noise ratio. And we had similar expressions in both the uplink and the downlink. There were some key differences such that we have the power for the downlink here, and in the uplink we have the power for the uplink. We can also see that in the interference terms we have a beta I here, which is describing that in the uplink the interference is dependent on the strength of the other user's channels. While in the downlink we have beta K here, which is the user that we are considering. So this is that the interference in the downlink comes from the base station through your own channel. But apart from that, the expression is rather similar, but it's describing the number of bits per complex sample that we can transmit when we use a channel for transmit data. But within each coherence interval, we also need to learn the channel. So we have been talking about how we do that. We are sending these pilot signals that are of length tau p, and we can view that as a pilot overhead. We need to spend that in order to be able to transmit the data and achieve these type of capacity bounds. So out of the tau c samples in the coherence interval, tau p of them needs to be utilized to send the pilots. And therefore, we say that the net spectral efficiency is that we are taking these capacity lower bound and then we multiply with a factor that says what fraction of the coherence interval are we actually being able to dedicate to data transmission. And that is the full fraction 1 minus tau p, which is the length of the pilot, divided by tau c, which is the length of the coherence interval. So this is the fraction of a coherence interval used for pilots, and 1 minus that fraction, that is the fraction that can be used for data transmission. We multiply both the uplink expression and the downlink expression with the same factor here to say that this is the net spectral efficiency, the number of bits per complex sample that we can communicate if we are looking at the coherence interval as a whole. And actually this expression is also saying that if we use the entire coherence interval for pilots plus uplink data, well then this is the spectral efficiency that we can achieve. And if we use the whole coherence interval for pilots plus downlink data, well then this is the net spectral efficiency that we are achieving. And then if we would like to send both uplink and downlink data, well we need to take these two expressions and multiply with the fraction that we are dedicating for the uplink and for the downlink data. So if we split equally, then we multiply with 1/2 in front of both of these expressions. In many cases, we are sending more downlink data than uplink data. So, for example, we could have 2/3 here and 1/3 in front of this expression. But the important thing is that this is how it works. And this tells us something important, namely that the larger tau p is, the smaller this fraction in front of the logarithm is going to be. And that is going to be a limiting factor that we should bear in mind in this lecture. because now we will move to considering not one cell as in the previous lectures, but multiple cells. And a canonical way of describing this type of cellular network is to say that each cell contains one base station and k users, and it has an hexagonal shape. So user 1 to k-1 and capital K. And here we have the base station with M antennas. So each cell is having the same shape as before, but now we have multiple of them next to each other. And we can operate every cell in the same way as before, but we will see interference between the different cells, both during data transmission and when we're estimating the channels by sending uplink pilots. So we need to complicate the notation, unfortunately, in order to consider these multiple cells. So say that we have capital L different cells. When we now are talking about one base station and one user, these might be located in different cells. So let's talk about the base station L, that is the base station cell number L, and user K, which might be located in other cells. This is user K in cell L prime. In every cell there is one user that has the index K, because in every cell there is capital K users. And then the channel between this base station L and user K in cell L prime is described by a vector. L as a superscript here is described in the base station's location, and L prime is the cell of the user, and K is the index of the user locally in that cell. And this is an m-dimensional vector that contains then these m scalar values describing the channels from one of the base station's antennas to this user. So we add this additional 1 to m as superscripts. So the notation that we are using is like this. G is one channel coefficient here, a scalar number, and in the superscript we have the base station index first, followed by the base station antenna number. And in the subscript we have the user cell, and then we have the user index. This is the notation for one channel coefficient between one base station antenna and one user. If we put them into this vector here to describe the channel from one entire base station to the user, well then we put them next to each other here, 1 to m, and then we, in the notation here, we have boldface to say it's a vector, and we don't need to have that extra superscript because we know that we're going to have all of the base station antennas. So here's another way of describing it. We are considering a base station in cell L that have M antennas, and we have a user K in another cell L prime, and the channel between them is this vector GL in the superscript, L prime K in the subscript. So this is the channel. And we can then create a lot of different channel vectors like this between every base station and every user in another cell. So there are K users in every cell, we have L cells in total. So L times K users in total. And we will use this Rayleigh fading or IID Rayleigh fading models again. So we have the channel vector that we were describing here. It's going to be complex Gaussian distributed. It has zero mean. It has an identity matrix as its covariance matrix, and the variance for every element is beta, just as before, but we have L prime K as the super and subscripts here. So this is also saying that we don't have any base station antenna index here because we have the same variance for all of the different base station antennas to a particular user. But the beta parameter here will be generally different between every user and every base station. If you compare this with the notation we used in the previous lectures when we considered just one cell in the network, well then the base station and the user was in the same cell. We didn't have any particular index for those cells. So therefore we could just remove the L and L prime. We get beta K and G K. So that was the same notation that we used before, but we could omit the base station and user cell indices. But apart from that, it's the same structure. We just need more super and subscript to describe everything here. So please bear with me in this lecture. We will going to have a large number of additional indices, but the structure will be the same. So if we talk about the uplink now and look at this multi-cell MIMO system, the received signal that we are considering at the base station, well, we need to consider a particular base station. Say that we had the base station in cell L. There we are receiving a signal Y, and we need to have a subscript L to describe that this is the signal in cell L. And the received signal is this m-dimensional vector. It contains YL1 to YLM, so these are the received signal at the different base station antennas. Then we have one signal part here that is describing the received signal from transmissions going on within our cell. So we have row uplink, which is the maximum power that we can transmit with in our cell. Then we have a channel matrix, GLL, so it's from the users in cell L to the base station in cell L. And in general, we can have a channel matrix GLL prime that is containing these different elements that we had defined on the previous slide. So every column here is describing the channel from one user to all of the antennas at the base station. In particular, from user 1 here in cell L prime to the base station in cell L. And it goes on like this for user 1 to user K. And then here we have a transmitted signal from the different users in cell L, XL, and it contains XL1 to XLK. So it's a k-dimensional vector, just as this channel matrix is an m by k matrix, so we can multiply them together. And we then have the signal from user 1 in cell L down to the signal from user K in cell L. And each user signal is power limited, such that if we take the absolute value square and compute the expected value of it, it should be small or equal to 1. So it's normalized because it's this row uplink term here that is describing the total power that the user can use. And then if it selects a 1 here, then it's using the full power. If it selects something smaller than 1, well, then we are not using all the powers that is available for us. So this signal term here within the own cell looks the same as in the previous lecture, just that we have added this additional LLL just to point out that this is the signal transmitted from users in the cell to the base station in the same cell. Then we have an additional term here which looks similar, but this is interference from users in other cells. So we still have the row uplink term here with the square root. We have a summation over the different cells. L prime goes from 1 to capital L, but is not equal to the cell where the base station is. And then we have this channel matrix from users in cell L prime to the base station in cell L. And then we have the transmitted signals XL prime. These are the signals sent from the users in cell L prime. So this is the interference. And finally, we have the noise vector, WL. It contains WL1 to WLM, so it's an m-dimensional vector. And we assume that we have normalized the noise to keep it simple. So this vector is complex Gaussian distributed, and it has a covariance matrix, which is just an identity matrix. So every element of this vector is independent and have variance 1. Okay, so this is the uplink multi-cell MIMO system model. It's have the same structure as we had for one cell, it's just that we need to add up terms from multiple cells and we need to have these additional indices to keep track of. If we start now with the first thing we need to do in every coherence interval, namely to transmit the pilots. Then previously we assumed that we have k users in the cell and they were all sending orthogonal pilot signals, which required us to have a number of pilot dimensions, tau p, which is larger or equal to the number of users, k. In most cases, it might be enough to have tau p equal to k in the single cell case, because tau p is the number of orthogonal pilots we can create. But when we consider a cellular network, that is when it's very useful to have more pilots than we have users within the cell, because we have so many additional users if we're considering all the cells. We have L times k users in total. And we can't give orthogonal pilots to all of these users, because then we will need to have L times k orthogonal pilots. Say that we have 100 cells and 10 users in every cell, well then we will need to have 1,000 pilots. And typically a coherence interval only contains, say, a few hundred of complex samples. So it won't be possible to, within one coherence interval, let all of the users have orthogonal pilots. That means that we can say that within each cell we should still have orthogonal pilots, so that the k users there can transmit their pilots. We can estimate the channels locally without getting any strong interference between the different users. But since we can't assign orthogonal pilots to all of the users in the entire network, we need to instead say that the same pilot as in one cell should be reused in other cells as well. And we can do this in different ways. We can define what is called the reuse factor, which is telling us how frequently are we using the same pilots again. So if we have an n reuse, which is equal to 1, that means that in every cell we use the same pilots. So if we look at the center cell here, we have k pilots, then the same k pilots are used in next cell, and the next cell, and next cell, and so on. And that means that we need k times n reuse pilots in total. So k times 1, so just k pilots. Another option might be to use a larger reuse factor. Say that we have 3 as a reuse factor. That means that we have 3 times k pilots. So we can divide those pilots into 3 different groups and assign them to the different cells in a different way. So a good way is to make sure that the neighboring cells are not using the same pilots, because that means that the interference will be less, because we have some natural physical distance between the cell where the pilots are used and the next cell where the same pilots are being used. This is illustrated here. The yellow cells are using the same pilots, and we see that if we have the yellow cell here in the middle, then none of the neighboring cells are using the same pilots. So we have cells at other places here that use the same ones, and we have a regular pattern here. And this is one of the reasons to consider hexagonal networks, because there we can have this type of regular patterns where we, for example, by having a reuse factor of 3, we could paint the colors like this. Then we have 3 different sets of pilots. So in addition to the yellow pilots here, we also have green pilots and red pilots. So these are making up these 3 different sets of k pilots. So the red cells are satisfying the same requirement, so none of the neighboring cells to a cell using the red pilots are also using those pilots. So we also get this natural physical separation between the cells that use the same pilots. And then we have the green cells that satisfy the same requirement. And we can also have a reuse factor of 4. In this case, we are pushing away the cells that use the same pilots even further away. We have 4 colors: red, blue, green, and yellow. And by increasing the reuse factor, we can make this distances between the cells that use the same pilots larger and larger. And under the assumption that we have hexagonal cells, there are only certain pilot reuse factors that are able to create this type of regular patterns that we are illustrating here. So 1, 3, 4, the next one is 7, and so on. And in the Fundamentals of Mass and MIMO book, those are the 4 cases that are considered. But you can use larger numbers than that, but in most cases it's these smaller numbers that are of practical interest. And in traditional cellular networks from the 80s and 90s, before we were starting to use multiple antennas in order to separate users, then we couldn't control interference between neighboring cells in a good way. So then we used similar patterns like this to take the bandwidth and divide them between different cells. So that we, for example, had 3 different chunks of bandwidth that we assigned to different cells, so the neighboring cells weren't using the same one. Or here that we have 4 different chunks of bandwidth and we assign them to the different cells so that the neighboring ones are not using the same one. But the concept here is fundamentally different. All of the cells are using all of the bandwidth all of the time. But in order to make sure that we are estimating the channels well enough so that we can use our antennas in a good way, we allow ourselves to have this type of pilot reuse factors. So instead of having just k pilots, where k is the number of users in one cell, we have k times n reuse pilots so that we can make sure that the neighboring cells are not using the same pilot, and that way we get better channel estimation quality, and we'll look more deeply into that. But during the data transmission, all of the cells are transmitting at the same time and all the cells are interfering with each other. We just need good channel estimates in order to separate the users in different cells using our multiple antennas at the base station. So what are then the impact of this pilot reuse? Well, since the same pilot sequences are sent by multiple users, this creates interference during the channel estimation. Previously, during the channel estimation, we only saw the channel plus noise. But now we see the combination of multiple channels. So say that these two users here in neighboring cells are using the same pilot. And they're sending that pilot to their base station, but at the same time this other user is sending the same pilot. So we are getting this type of interference between the different cells. So the desired signal are the solid arrows here, and the interfering signals are the dashed arrows. And this is creating a phenomenon called pilot contamination, which means that the base station can't separate which part of what it sees that is the channel from the user in another cell, and which part is the channel from the user in the own cell. And this will create additional interference, which we will see later on. But in order to model this properly and analyze it, we need to figure out which of the cells are contaminating each other's pilot transmissions. We say that the set PL is a set of cells using the same pilot at cell number L, including this cell itself. So if we had a pilot reuse factor of 1, then PL is containing all of the cells in the whole network. If we have a reuse factor of 3, and cell L is yellow, well then PL contains all of the yellow cells. And then it goes on like that. So remember now, when we did the channel estimation previously, we were considering estimating a Gaussian variable in Gaussian noise. So the Gaussian variable were the channel, and the Gaussian noise was just thermal noise. So we were receiving something which we call Y. We had a power P, which is a constant. We have a unknown channel, G, with a variance beta and a complex Gaussian distribution. And then we had some W that is disturbing the channel estimation. And it was complex Gaussian, and previously it had a variance 1, but now we will call it sigma square, because we will later put into W not only thermal noise, which has variance 1 in our model, but also other types of signals that are also Gaussian distributed. So when we consider channel estimation, we were considering to minimize the mean squared error, so the difference between the true channel and the estimate in absolute value square and on the average. And the minimum mean squared error estimator took the form where we say that G hat is equal to Y, what we observed, multiplied with a scalar that contains square root of P times beta, divided by, previously we had 1 from the noise term plus P times beta, but now we get the sigma square here instead. But apart from that, the expression is exactly the same as before. And we just need to keep track on where did we have a 1 and put a sigma square there instead. So the estimation error, G tilde is equal to G hat minus G, is going to be complex Gaussian and have a variance that looks the same as before. It was beta minus P times beta square divided by, previously we had a 1, but now we have a sigma square, and then plus P times beta. And the estimate that we compute here, since Y have a certain random distribution, it's also complex Gaussian distributed, has P times beta square in the numerator, and we had a 1 here before, now I have a sigma square, and then plus P times beta. And these were independent random variables. We will now use these results to do the channel estimation in the multi-cell case. So we are sending the pilots in the uplink in the same way as in the single cell case, but only some of the cells are sending the same ones. So after we do the despreading operation at the base station in cell L, we have the following received signal. It contains a summation over all of the cells that use the same pilots as cell L, including the cell itself. We have the channel matrix from the users in cell L bis, which was the cell index that we are summing over here, to the base station that is receiving in cell L. And here we have the scaling factor, we have the total transmit power times the length of the pilots, and we square root of that. And here we have the noise matrix containing independent Gaussian variables with unit variance. One of the channel matrices in this summation is GLL, the one that the base station in cell L will like to estimate. And it's Gaussian distributed, they have the variances that we talked about previously when it comes to the channels. And the rest of the terms in the sum is going to be interfering with us. But also those channel matrices are Gaussian distributed. So the sum of those channel matrices multiplied with this factor plus the noise is going to be Gaussian distributed. So say that base station L is interested in estimating the channel from its antenna M to user K in cell L prime, which is one of the cells inside here. Well, what it can do now is to compute the MMSE estimate, and in order to do that, it should use the same formula as we had on the previous slide. We should take in the numerator, the factor in front here, square root of tau p rho uplink. It should take the variance of this unknown channel that it would like to estimate, which is beta L L prime K. And then in the denominator, we should take the variance of the signal that we are interested in, tau p rho uplink times beta L L prime K. So that's something that shows up in the summation here. And then we should have the variance of all of the interfering things which are also Gaussian distributed. We get the 1 from the noise matrix, and then we get this summation here where we should exclude the desired user, but we also have that desired user within the denominator before, so we get exactly the variance of this. So this is actually the variance of a particular element, this matrix. Which one? Well, the one on place M, K. So mth row and kth user. So that is how we are finding this particular element from the matrices here on the nth row and kth column. And this channel estimate is computed like this, and if we are interested in its variance, well then we are computing it in exactly the same way as I described in the previous slide. It's going to be Gaussian distributed. We say that it has variance gamma L L prime K, and it has this expression here when we have the power of the signal here, tau p rho uplink first, then we have the variance of the element we would like to estimate, squared, and then we divide by the same term here the variance of this term here. And if we are interested in estimation error, well then we take the estimate minus the true value, and we get the estimation error, and its variance is going to be the original variance of the true channel minus this gamma term, which is the variance of the estimate. So we have the same structure in our estimates here as we had in the single cell case, with the main difference that we have many more indices to keep track on when it comes to which cells we are considering, which base station we are considering, and that in the denominator we are not only getting the variance of the received signal from the user that we would like to estimate the channel of, but all of the users that send the same pilot. And for future use, let's put all of this estimate for user K in cell L prime, estimate that base station L, in a vector like this. So it goes from 1 to m here in the superscript to describe the channels that we estimated to each of the m antennas at this base station. And we should remember this one because we're going to use it for the receiver processing. The fact that we have multiple users using the same pilot is creating what we call pilot contamination, and it has two main consequences for the performance of a massive MIMO system. So one is that we get a lower estimation quality. So what that means is that if we look at this gamma, which is the variance of the estimate, then we get this expression here where we have a summation over the cells that are using the same pilot. And if we would neglect all the terms in the sum except the one where the user that we're estimating the channel of is, then we will get this expression, which is the same as we had in the single cell case, except for the additional indices here. And when we neglect this, we are removing terms that are positive from the denominator, which means that we get a larger estimation variance, which is a better thing. So pilot contamination leads to a lower quality of our estimate as compared to not having any contamination at all, and that is seen by having a smaller variance of the channel estimates. The second important consequence is that we get correlated channel estimates. That means that when we're estimating here the channel of user K in cell L at the base station in cell L, then if we are considering another user that is using the same pilot and that user is located in another cell, then the estimate of our desired user is correlated with the channel of this particular user. What does that mean? Well, when we are computing this estimate, we are taking a scaling factor multiplied with a received signal that contains the desired channel, the G here without the hat, and also the channel here from the pilot interfering user. So this expectation here, when we multiply these two together, with the conjugate and we compute the expectation, well, this first term is contained in the second term multiplied with the scaling factor. So this term is going to be non-zero. While if we were removing the hat here and took the true channel, these are going to be independent and zero mean, so then you would get an expected value that's equal to 0. But when we use the estimate, we don't get something that's 0. And this means that if we are summing up over all of our antennas at the base station and compute something like this, then we get something that is proportional to the number of antennas if the two users use the same pilot, while we get something that is 0 if they're using different pilots, because then this estimate here won't contain the channel of this other user when they're using different pilots. And this will lead to additional interference, because when we are using the channel estimate of this other user in order to process our received signals, we will create terms of this kind that are interfering, and that is going to be larger than if they were not correlated. We will now consider the uplink data transmission, and for the base station in cell L, we are receiving this signal that we defined earlier. And we have XL and XL prime, those are the signals transmitted by the users. And we now would like to select them to contain data. And we say that XL is selected as QL multiplied with the diagonal matrix here. QL contains QL1 to QLK. These are the data signal transmitted by the users in cell L, from user 1 to user K. And it's a k-dimensional vector. And each of those ones are multiplied with the power control coefficients, eta L1 to eta Lk, and these are coefficients between 0 and 1 that tells us are we transmitting with the full power, rho uplink when we have a 1, or no power at all when we have a 0. We take the square root of this diagonal matrix, which means taking the square root of each of the eta terms. We multiply the matrix with QL in order to multiply them pairwise, and then we get a signal transmitted by the users in cell L. And the base station in cell L is receiving all of this, but it's only interested in the signals from its own users. And in particular, let's consider user K in cell L. Then the base station assigns a receiver filter, which is an n-dimensional vector, ALK, for user K in cell L. And we should select the receiver filter so that when we take an inner product with the received signal, like this, we are getting something that's similar to the data signal sent by user K in cell L. And one option is to use maximum ratio processing, where ALK is just selected as the estimate that base station L have of the channel from user K in cell L. This is just one option. We can scale it in different ways, it won't make any difference. We can also call it maximum ratio combining, but this is the only choice where we consider in this lecture, because in that case we can compute a lower bound on the capacity in the same way as we have done in previous lectures. We're just going to have these additional terms with interference, which means we have additional expectations to compute, but in the end we are getting an expression that looks very similar, namely like this. So this is the uplink capacity lower bound with maximum ratio processing, and it is for user K in cell L. It has the shape log2 or 1 plus a ratio here is signal to interference and noise ratio. In the numerator, we have a term which is the desired signal term, and we say it's coherently combined because we get the M here, the number of antennas. We have the power transmitted by this user, rho uplink eta Lk, and then we have the estimation quality of the user, gamma L Lk. Then in the denominator we have three terms. The first one is non-coherent interference from all the users. And that is something that we had in the single cell case as well, but now we're summing over all the cells and all the users in those cells. Previously we only had one cell. And we have the power, rho uplink eta L prime K prime. This is the power of the signal transmitted by user K prime in cell L prime. And then we have this beta term here, which is described in the large scale fading coefficient, or just the variance of the channel between the interfering user here and my base station. Then we have an additional term that is called coherent interference, and it's called like that because it also scales with the number of antennas just as the desired signal. And this is interfering signals coming from the pilot sharing users only. So we're summing up over all of the cells that are using the same pilot as my cell, and I'm excluding my cell because there I am the user that used the pilot. And it's only user K in those cells, because that's the same index as me, that is interfering. And the structure is otherwise the same. We have this row uplink times the eta parameter saying what power is that user transmitting with. And here we have the estimation quality of the channel from that user to my base station. And finally, we have a 1 here representing the noise variance. So pilot contamination is the new phenomenon that is appearing here, and it has two effects. One is that it creates this coherent interference term here, which we didn't have before. And it was just because we have pilot sharing users. When we're trying to estimate the channel of a desired user, we're estimating a part of the channel from another user as well. So when we try to coherently combine the desired signal, we're also accidentally coherently combining part of the interference. And in addition to that, pilot contamination is also making the gamma term of the desired user smaller due to the additional interference during the pilot transmission. So in summary, the capacitor lower bound have a similar structure. We still have a desired signal that is growing with number of antennas. We have non-coherent interference, but we have additional summation here over all the cells, and we have additional coherent interference. Let's now look at a downlink. And we are considering the received signal at the users in cell L. And that is a vector, YL, containing YL1 to YLK. So these are the received signal at user 1 to K in that cell. It contains, once again, 3 different parts. The first part here is the transmission of signals from my base station to the users in my cell. So here we have row downlink, which is the maximum transmit power. We have XL, which is a signal vector transmitted from that base station, containing XL1 to XLM. And if we take the square norm of that, compute expectation, it should be smaller or equal to 1 to say that we are not using more than this maximum power row downlink. And then we have the channel matrix, GLL. So it's defined in the same way as before, but we have applied a transpose here to say that now we are transmitting in the opposite direction from the base station to the users. Then we have interfering terms here coming from other cells. So we're summing up. L prime goes from 1 to capital L, but we are omitting the cell that we are considering now, the cell number L. And then we have the maximum power. We have the signal transmitted by the base station in that cell. Then we have the channel matrix from the base station in cell L prime to the users in cell L. And we have a transpose on that channel matrix as well in order to say that we're transmitting from the base station to the users. And finally, we have a k-dimensional vector, WL, containing WL1 to WLK. It's complex Gaussian noise. It has variance 1, so things are normalized. And when we are transmitting here, somehow these X terms here needs to contain the downlink data. And we will just consider one choice of XL, namely maximum ratio precoding, where XL is a summation over all of the users in the cell. And for each user, we have a QLK, which is the data intended for user K in cell L. We have a power control coefficient that tells us which fraction of the total power in the cell is assigned to this user. And then we have a precoding vector here, which is normalized so that it has a average squared norm that's equal to 1. So this eta parameter is saying how much power we actually assign to different users. And we have selected this precoding vector based on the maximum ratio principles. We take the estimate of the channel from the base station in cell L to me as the user, and then we are normalizing that vector. And when we have selected something like that, we can compute a capacitor lower bound in the downlink in the same way as in the previous lecture. We will have a desired term coming from here, and we will have interference from within the own cell just as previously. But we also have interference from other cells that we need to consider. So we just get additional expectations to compute. And finally, we have the noise here. That is the same as before. And if you compute everything in a similar manner as before, this is the capacitor lower bound that we get with maximum ratio precoding for user K in cell L. And it's log 2 or 1 plus a signal to interference and noise ratio, where in the numerator we have the desired signal, which is coherently combined thanks to the beamforming. So we have this beamforming gain of M. Then we have the downlink power assigned to this user, and we have the estimation quality of the channel at this base station that is serving it. Then in the denominator we have 3 terms. The first term is non-coherent interference, as we were expecting. we have the transmit power, rho downlink times eta L prime K prime. This is the power that is assigned to user K prime in cell L prime. And here we have beta, which describes the large-scale fading coefficient or the variance of the channel from the base station L prime that's transmitting to this user to me as a user. Then we have coherent interference from the pilot sharing users, or due to the pilot sharing users, because now it's the base station in the cells that are using the same pilot as me that is interfering additional to me. So when they try to beamform to their user that uses the same pilot as me, then they are accidentally beamforming some of the signals towards me as well. So I get a beamforming gain of M, rho downlink, eta L prime K. This is the power that is assigned to user K, so it's a user with the same index as me, but in another cell, L prime. And here is the estimation quality of the channel from the base station in cell L prime to me as user. And finally, we have the noise here. So we can say that pilot contamination have once again two impacts here. It reduces the estimation quality, gamma, and it creates this additional coherent interference that we didn't see when we considered just a single cell with orthogonal pilots. If we compare the uplink and downlink expressions, then in the non-coherent interference terms in particular, we can see how they are different and also similar. In the uplink, we have a summation over all of the users. We have the power that is transmitted rho uplink times eta L prime K prime. So it's the transmit power of a particular user somewhere. And then we have this beta term that is describing the channel from that user to my base station. In the downlink, we have instead rho downlink times eta L prime K prime. It's the same notation as over here, but it's actually a different parameter. We can set a different value there because this is saying how much of the downlink power that is assigned to a particular user. We still have a summation over all of the users. We still have a beta term, but with different indices. This is the large-scale fading coefficient from base station L prime to me as a receiving user. So the differences are that we should switch rho uplink to rho downlink when we go from uplink to downlink, and we should switch the indices here on the beta terms. So where we have primes, we should not have primes, and the other way around. And this is just describing again that in the uplink, interference comes from each of the users to the different base stations, and in the downlink, interference comes only from the transmitting base stations. Finally, let's have a look at what happens with the capacity expression when we have a large number of antennas, one of the extreme effects of massive MIMO. So in the uplink, we had this capacity lower bound for user K in cell L, and if you let the number of antennas grow large, it goes towards infinity. We should have a look at the two terms that contains M. It's these two terms. And all of the other terms will be negligible compared to these two terms, which means that this ratio here will converge to a ratio that we're getting when these noise term and non-coherent interference term disappears. Additionally, the M will of course cancel out each other. Also the rho uplink terms cancel out each other. We have the eta terms left, and the gamma terms, we will get ratio between those ones, and if you look at how the eta terms looks like, they actually have the same denominators. So they will also cancel out, and in the end you can show that this is the limit that you will approach. So even if we have a huge number of antennas, it won't be like in the SIMO channel where the capacity was growing as the logarithm of the number of antennas, but here we are instead approaching a upper limit, which is characterized by the eta parameters that says how much power that we are transmitting with. And then we have the beta terms squared, and those squares were something that appeared in these different gamma terms. So the upper limit is determined by something that comes from my own cell and something that has to do with these pilot sharing cells. So we are summing over those cells that use the same pilots as me, and then we have how strong are their channels from the user to my base station. If we want to make this limit larger, we could actually play around with these pilot reuse factors. So if we are increasing the pilot reuse factor, we should remember that, okay, if I'm the cell here in the center, then I get pilot contamination by summing over all of these other yellow cells. So this term is created in that particular way. And if I'm going up to a reuse factor 4 here, now I'm a red cell. The cells that are interfering with me, that are summed up in the denominator, they are further away, and there is also fewer of them in the vicinity of my cell. we are simultaneously increasing the estimation quality because we push the interfering cells further away, and we also have fewer cells that are going to create coherent interference. So we have these two effects again. But of course, the negative effect of increasing the reuse factor is that when we are not only talking about the capacitor lower bound, but also include this pre-log factor that we had when we talked about the net spectral efficiency in the beginning, this 1 minus tau p divided by tau c, that term will become smaller as we increase the reuse factor. So there's also reasons to keep down on this reuse factor. So in summary, we have considered massive MIMO in cellular networks. We saw that we get similar capacity lower bounds as in the single cell case, but we have more complicated notation because we need to keep track on in which cell is the base station and in which cell is the user that we're considering. Moreover, we get this new phenomenon of pilot contamination, which reduces the estimation quality because we get additional interference when we are transmitting the pilots. And pilot contamination also creates additional interference terms that are coherent, meaning that they are scaling with number of antennas, and those are appearing in the denominator of the capacity lower bounds. And these two effects are both reducing the capacity lower bounds value as compared to the single cell case. So that is the end of lecture number 10 in multiple antenna communications.